Hello everyone, welcome on this e-learning platform of Apex Institute of Physics. In this video, we will be talking about some important points. Like first is equipotential surfaces. So how we define equipotential surfaces and what the equipotential means. So the meaning of this word is equipotential. That means equi means equal, potential means potential. That means collection of all such points that have a same potential is known as equipotential surface. So we collect all the points having the same potential, and whatever the surface we are going to create, that surface is going to be equipotential surfaces. For instance, let's say we have a point charge. So due to a point charge, in case of a point charge, we know the potential is given as V is equal to kq upon r. That means if we are at a particular distance from the point charge, all the points located at a same distance from that charge will have a same potential. That means surrounding to a point charge, we will have a surface which will be equipotential surface. So if this is a charge q located, you can imagine this kind of particles having the same distance will be equipotential in nature. Now if we collect all these points, which is a particular distance from this charge, let's call that is r, then we will find such points collection will be forming a spherical surface. That means because of a point charge, we have spherical surfaces which are going to be equipotential in nature. So equipotential surfaces will be spherical surfaces, which I can show by this picture. Here the q charge is located at the center. So because of this q charge, this sphere, which is so shown by a dotted line, this will have a particular potential. We can call it, this potential is V1. So all the particles on this sphere will have a V1 potential. So that's a spherical surface, is equipotential surface. If we come on this sphere, this might have a potential V2. So all the points will have a V2 potential. So this middle sphere is also equipotential surface. Similarly, this outer sphere may have a potential V3, and that's going to be equipotential surface. And these arrows are indicating the direction of field. As we talked in the previous video, if we move in the direction of field, potential decreases. So we can claim V1 is highest potential, then V2, and V3 is the least potential. But whatever the points on this outer sphere is, all the points will have a V3 potential. So they are called equipotential surfaces. So for point charge, we have spherical equipotential surfaces. Similarly, if we have a line charge, long line charge, so due to line charge, can you imagine what kind of equipotential surfaces are going to be there? So we know due to a line charge, if it is long enough, then a field is radially outward, right? So symmetrical surfaces are going to be cylindrical. So we will have a cylindrical equipotential surfaces that we can see in this picture. So due to line charge, we will have these kind of surfaces. So let's say this is a line charge, which is long line charge. So surrounding this linear charge, there is going to be the cylinder, the inside one. All the points of the cylinder are equidistant from this line charge. So all the points will have a same potential. Let's call that as a V1 potential. So all points will have a V1 potential. Similarly, if we draw another cylinder, so this V2 will have this cylinder, outside cylinder will have a potential V2. That means it will be potential of all the points. So due to a line charge, we will have cylindrical equipotential surfaces, right? So this is how we can find out the equipotential surfaces. Because a point charge is spherical in nature, due to line charge, they are going to be cylindrical in nature. And the third distribution could be plane sheet distribution that we have talked about earlier. So let's say this is a large sheet, and because of this large plane sheet, which is two-dimensional sheet, let me think it. So because of this, if somebody asks how much this equipotential surface, or how the equipotential surfaces are going to look like, so we know if this is a large plane, so we will have a plane surfaces. Maybe I'm drawing with a different color. So if we draw a surface over here which is parallel to this plane, this surface will have a same potential, this another surface will have a same potential. So we can say the potential of this surface might be V1, so potential of this surface might be V2. So these surfaces are going to be planar in nature. So here equipotential surfaces are going to be plane. So these three types of surfaces are important for us: spherical equipotential surfaces for point charge, cylindrical equipotential surfaces for line charge, and planar equipotential surfaces for plane charge, right? After learning equipotential surfaces, there is another important point that we are going to discuss in this slide: testing conservative nature of electric field. We know this electrostatic field is a conservative in nature. That's why we define the potential corresponding to this field. Now, how we will decide whether a given field is conservative or not, or whether a given field is representing electric field or not? So there will be a question. They will provide a field. Let's say a field is given to us in this manner: E is as a vector is equal to Ex I cap plus Ey j cap plus Ez k cap. And they may ask you identify whether this expression is representing the electric field, or they may ask identify whether this given expression is conservative or not. So to check whether a given expression is conservative or not, what we need to do, we need to find this determinant. So we will be solving one determinant. So for that sake, we will be using two parallel lines to make a determinant. So let's say this is one line, this is another line, and within this line, within these two lines, we will be writing this terms. In the first, we are going to write I cap, j cap, k cap, and then we will be writing the partial derivatives del upon del x. In this we will write del upon del y. In this next we will write del upon del z. And in the last row we will be writing the x component of given expression, y component of given expression, z component of given expression. And by using the rules of opening this determinant, we will finding out what this value is going to be. Now if this value is going to be equal to 0, so we will find this determinant, and let's say this determinant we can call it as del cross, and this we can say del v, or let's not write that complicated expressions. We call this as a determinant, and if this determinant's value come out to be 0, so let me write here if this determinant is come out to be 0, then we will claiming the expression that has been given is conservative, and if it is conservative, then it can represent electric field. However, if this does not come out to be 0, then we will say it is non-conservative, right? So else E is, or expression is non-conservative in nature. So this is how we can test whether the expression is conservative or not conservative. We will have an example to use this method to test whether the field is conservative. But this is the method that is important for us to understand. So let's say there is an example. It says E is given as, let's say it starts like y, z, I cap, zx, j cap, plus xy, k cap. This is the given field, and it is being asked, check whether given E or given expression is conservative, or that represent a conservative field or simply field. So I'm writing is conservative. You can pause this video and solve it, and then you watch the solution. So solution will be just following the idea that we have just talked about. For that sake, we need to draw a determinant. So for that sake, we need to have two parallel lines, and within these lines we need to fill these quantities that are required. So this will have a first row I cap, j cap, k cap, and in the second row we know these partial derivatives with respect to x, with respect to y, with respect to z, and in the last we need to write ex, ey, ez. Here the ex is yz, we can identify, and this ey is zx, and then the last is xy. So if we consider this and we expand it, so we know how to expand this determinant. So I cap will have consideration for these terms. So this will be del upon del y in bracket xy minus this cross multiplication will lead to del upon del z in bracket zx. So that will be the coefficient of I cap. Then you know we need to expand with for j, so there has to come a minus sign, and for that say we will not consider this column, this row, so they have to multiply it, cross multiplication, so del upon del x, and that del upon del x will be over xy, and then this cross multiplication, that will be minus del upon del z, and it will be applicable on yz. And the last term we will finding is going to be k cap, and then for that sake this row and this column will not be considered, so cross multiplication of these things, that means del upon del x zx minus del upon del y yz. So that's going to be the k cap. Now using this mathematical rules, we are going to simplify this. So I cap coefficient we will be having. Now this is a partial derivative, so x will be treated as a constant, y derivative will be 1, so that will become x minus, here z differentiation will be 1, and that will lead to x, so I coefficient will be this, minus when we come to the z, so this x will become 1, so this becomes y, minus z becomes 1, so this becomes y. Similarly we will come to the k coefficient, x derivative will become 1, so z will treat it as a constant, here y will become 1, z will be treated as a constant. If we see carefully, so this is coming 0 I cap minus 0 j cap minus or plus 0 k cap, that means we are getting it as a 0 vector. Since it is coming 0, we can claim the given expression is conservative, so E is conservative. So this is how we can check whether a given expression is representing a conservative or not. That means this expression can represent electric field. And if it would have come non-zero, then we say this expression cannot represent electric field, because for that sake it has to be conservative nature, right? So these are the points that we have discussed in this video. Please rewatch, make your notes and follow it. And thank you for watching this video. Have a good time.